thanks for the introduction. Yes, this is a joint work with my colleague, Cryan, and my student, Giorgos Mousa. George was supposed to give the talk, but unfortunately he fell ill, so I came. Especially thank you for coming, for being the being the last day, and also for coming to a talk with an intimidating title. I don't expect, like many of you know what this log-Sobolev means. So instead, I will try to give you something more concrete. I will give you some concrete consequences of our result. Last talk is about sort of a continuous random walk for continuous log-concave distributions, like uniform distribution in the polytope. And this talk will be about random walk for discrete log-concave distributions. I put the quotation marks here because, a priori, it's not even clear what should a discrete log-concave distribution be like. And in fact, we arrive at the right definition after quite a while. And I will focus on two results. Both are consequences of this so-called log-Sobolev inequality. The first is a tight mixing time bound for a very natural Markov chain, which converges to the uniform distribution over basis of a matroid. And the second one is a sub-Gaussian concentration bound for Lipschitz functions, again, over random basis of a matroid. So these log-concave distributions are very related to matroid. And let me briefly remind you what a matroid is. I believe most of you know. Here I'm taking there are many equivalent definitions. I'm using the independent set definition. So matroid is sort of a combinatorial abstraction of linear independence. The empty set must be independent, and the independent set must be downward closed. And they should satisfy something called the argument axiom, which is sort of equivalent to the exchange axiom for like basis, which is probably a more popular definition. And all of the maximal independent sets have the same size, and therefore they are also maximum. And these form the basis, set of bases. And the size of the ground set will be denoted by n, and R will be the rank, namely the size of the basis. So here's the example. This is a graphic matroid. So here the ground set are the edges, and the sort of independence is for not having a cycle. And so bases are spanning trees, and this can be represented by vectors over F2. However, you should notice that Nielsen last year showed that almost all matroids are not representable. So this is definitely not what a typical matroid looks like, but I mean, that's the only thing I can draw. And I will use graphic matroids for the running example, but all of our results apply to any matroid. And there are many questions related to matroid. In particular, this talk will be on sort of how to efficiently sample a basis uniform at random. And okay, so there's something not clearly defined here because what's the input, right? Matroid may have exponentially many independent sets or bases. What's the input? Input will be the ground set and an independence oracle. So given a set of elements, I can ask the oracle, is this independent? And the standard approach to do this sampling question is Markov chains or random walks. Here is a very natural one, widely studied, called basis exchange walk. So basically, we start from some fixed arbitrary basis, and at every step, I uniformly at random choose an element, I remove it, I go to a smaller set of size R minus 1, call this S, and then I want to go back to a basis. So I will have a number of choices, and I uniformly at random pick one of the choices. As you can notice, the second step is not sort of a constant time. It seems you cannot easily implement it in constant time. But I will focus on this walk, so like these two steps will be considered as like one step in the inner bound I stated. Although to implement the second step here, I may need to list all the elements. I check whether with S this is a basis or not, and basically I may need as many as n oracle calls. This can also be viewed as sort of a random walk over, maybe lazy random walk over one skeleton of the matroid polytope or over the basis exchange graph of the matroid, basically the same thing. what I will be interested in is the mixing time, which is a way to quantify the convergence rate of a Markov chain. So I have this chain, and it will converge to the uniform distribution over basis. However, the question is how fast does it converge? And the mixing time is basically the first time the chain, here P is sort of denotes the transition matrix. The initial distribution is pi 0. So the first time T is such that the total variation distance falls below some epsilon. Epsilon can be arbitrary. So this is the mixing time. And so let's see some example of this chain. So here is a spanning tree example again. I have this spanning tree. I choose add uniform at random to remove. I remove this guy. Now I have basically I form a cut here. I have 5 edges possible. I want to add back one of the 5 edges, choose one at random here. And then I remove another edge. Maybe I pick the top left one. And then I have 2 choices. I add one back. Okay, so this is basically how the Markov chain goes in a graphic setting. Here is another sort of simpler example. I have a path of sort of length r. And well, except that each step of the path, I have 2 parallel edges. Again, I have randomly removed an edge, and then I will have only 2 choices to add it back, add something back. Then I remove an edge, add something back. So this is actually a very simple random walk, very widely studied. If you stare at it for a little moment, you realize this is the lazy random walk over the Boolean hypercube, 0, 1 to the r. And in particular, this matroid has rank r. You have r edges here to be a spanning tree. And the ground set has like size 2 times r because I have 2 choices for each step. And this random walk has mixing time basically half r log r, which is widely known. So okay, this is very fast mixing. The question is, what about the general matroid? And what we showed is that for any matroid, basically this upper bound of r log r is true. So more precisely, our bound is r times the log of the number of bases plus some term related to the epsilon. Epsilon is usually a constant or like 1 over n, and say, this is like a log factor. Because the number of bases is at most like n choose r, so this gives me r log r plus log n. And previously, basically earlier this year, there's a breakthrough result due to Anari, Liu, Cryan, and Vincent. They used some tools from Kaufman and Oppenheim. They showed that the mixing time for any matroid is like r times the log of the number of bases, which if you use this bound, you get like r squared times log n. So basically, our improvement is like from log of number of bases to log of number of bases. We have extra log, truly like TCS result. Okay, so although this is sort of a logarithmic, the number of bases is usually exponentially large. So this is it should be seen as sort of a linear improvement. And also this bound, you cannot improve it further because of the previous trivial example, you have r log r mixing time. And sort of studying the mixing time of basic exchange graphs has a long history, starting from like Mihail and Valdrani in the late 80s. And there are many results since then. And sort of our results unifies all of these. Some of these work are for special cases of matroids, and some are sort of a tight bound. Some are weaker bound, some are tight bound, but for special cases. And we sort of generalize all of them. Okay, so this is the first result. And the second result is the concentration bound. So again, let me have this pi being the uniform distribution. They have basic exchange walk. I have some function that defined over basis. So maybe I want to count the number of all the elements in my basis, let's say, in a random basis. So here I'm choosing a random basis, x, from the uniform distribution. The value of the function will be highly concentrated around the expectation. This is basically sub-Gaussian concentration. Here the R is the rank of the matroid. This V term, which has a complicated expression, is the maximum of one-step variance under the Markov chain. But if you have a sort of a Lipschitz function in this basic exchange graph, then this V will just be a constant. So for example, for my function of choosing count the number of all the elements in my basis, if you go one step of the Markov chain, the basic exchange walk, you can sort of change this value by at most 1, and therefore that's 1 Lipschitz, and this is like 1. So this should be constant, should be thought of as a constant, and then the main thing is like the R. So sub-Gaussian concentration for Lipschitz functions. Previously, there have been some results. The product distribution definitely has this kind of concentration. It's just Chernoff bound. And it's pushed towards like random variables with negative correlations. There's a work by Pimentel and Paris. They introduced some notion called stochastic covering property, which is some kind of negative correlation. And this result is actually implied by previous work for random variable with so-called negative regression. However, all these works sort of only captures the balanced matroid case introduced by Feder and Michael. They don't generalize to general matroid because matroid bases are not negatively correlated. So this is an example due to Seymour, Winkler, and Madhusudan. And so basically, I have a graphic matroid. Graphic matroid is known to have this negative correlation, and even something much, much stronger. However, I will truncate the graphic matroid. So this graph has like 8 vertices, so spanning tree has 7 edges. Instead, I will consider 6 edges subgraphs with no cycles. So basically, it's sort of a acyclic subgraph of exactly 6 edges. That's a truncation of the matroid, and it's still a matroid. However, if you consider that, then the probability that this edge E is in the random basis, condition on F being in the random basis is roughly 0.294, whereas the original probability of E being in the basis is 0.292. So this is not negative correlation. Okay, having F, condition on having F, the probability of having E increases. So negative correlation is not the right property you should look at in matroid setting. What's the right property? Right property is strong log concavity. And indeed, this is a very new notion. Well, old or new depends on your perspective. But it's until very recently, we realized this is sort of the right definition. And to define that, I need to introduce something more. So a log-concave polynomial is a polynomial whose log is concave. I take the Hessian of the log, and it's negative semi-definite. And the strongly log-concave polynomial is one where, after taking an arbitrary set of partial derivatives, I still get a log-concave polynomial. Okay, so it's not just the log-concave; it also log-concave is closed. This property is closed under taking partial derivatives. And the partial derivatives, later you can see that this sort of corresponds to conditioning, corresponds to contraction in matroid, and corresponds to conditioning in the distribution. So this is a very useful property. This notion was originally introduced by Giorgos, 2009, but apparently people didn't realize how important it is. More recently, some other notions also called completely log concavity were introduced by Anari et al. And the Lorentzian polynomial were introduced by Brandon and Heng. And it turns out all 3 notions are equivalent. They're defined in different ways, but they are all equivalent. And we are interested in distributions. So let's say I have a distribution over a subset of n elements, and I can write down the generating polynomial of the distribution. And I say this distribution is log concave if and only if my generating polynomial is log concave in the previous in the sense of the previous slide. And it's sort of a big result, as is in my mind. The uniform distribution over the basis of a matroid is strongly log concave. Again, this is shown independently by Anari et al. And Brandon. That's basically the motivation of them introducing these notions of log concave complete log concavity and Lorentzian polynomials. Okay. So we have these log concave distributions, and our main result sort of holds for any strongly log concave distribution are homogeneous. If it's not homogeneous, then we can do something with it. So the main thing is it has to be log concave. But okay, the modified log-Sobolev constant, I really don't want to define it because to write down definition it will take like 1 or 2 slides. But it suffice to say that the main results are a consequence of this inequality. And the missing time bound is quite straightforward. The concentration bound from some standard so-called Herbst argument. Okay. So this is something very complicated. I don't want to define it. I will give you sort of what is really what's the intuition behind it. And the intuition is the decay of relative entropy. Okay. So basically, the decay of relative entropy of the random walk is equivalent to these log-Sobolev inequalities. So in particular, what we actually showed in the paper is something like this. So for any distribution over this basis, after one step of the random walk, after I apply this P of basic exchange, my relative entropy, this or KL divergence between this distribution and the stationary distribution, uniform one, decays at a rate of 1 minus 1 over R. Okay? And in fact, what we showed is the first step of the random walk already decays the relative entropy. So you have something fixed, and whenever you remove an element, the relative entropy already decays. And the second step does not increase relative entropy due to Jensen inequality. So we have this decay with rate 1 minus 1 over R. So if you do that t steps, you get this raised to the power t. And the original, so initial relative entropy is log of the number of bases. Therefore, you can get the mixing time bound very easily from here, right? You get R to deal with 1 minus 1 over R, and you get log B together to cancel with the log B. And from Pinsker's inequality, the square root of the relative entropy is the upper bound of the total variation distance, and therefore you get the mixing time bound. So why does this improve over previous result? Previous result, Nari et al. And also like Kaufman, Oppenheim, they bound the spectral gap of this random walk. And the spectral gap governs the decay of a different distance, the separation distance, which is basically the maximum of the relative error between the two distributions. And the total variation distance is sort of upper bounded by this as well. And but the trouble is, if you consider the separation distance, the starting point is B instead of log B, because at first I have probability 1 on some particular basis. So this is 1 over B, which gives me B, the size of B. So if you have a spectral gap bound, then it's decay from B minus 1. Therefore, you need like R times log B time, and whereas relative entropy starts from log B, so it's converted fast. Okay, and what about proving this? It's a relatively simple induction argument, but to do that, we need to get some setup, which is this abstract simplicial complex structure, which I won't have the time to do that. And on that, and also sort of, as you can see, this relative entropy decay is very nice. It gives us very tight bonds. But there are not so many proof techniques. The only thing works basically is induction. And ours is no exception. But although it's sort of a different induction from before. To conclude, we have two results. One is the tight mixing time bound, and the other is sub-Gaussian concentration. Both are sort of implied by the decay of relative entropy or modified log-Sobolev, if you like the probability jargon. And about open problems, well, I mean, this the ability to sample a random basis and the concentration bound seems to be kind of fundamental. I would imagine it has some applications, although I can't tell you any application right now. So I want to maybe ask, is there any applications for this? Also, the basic exchange walk, the second step of basic exchange may take like n oracle calls, which is not good, right? The running time, if you want to do, say, sampling spanning trees using this, is very slow compared to other very fast spanning tree sampling algorithms. So can we do this faster? And also the natural next step is to sample common basis or common intercept of two matroids, consider matroid intersection problem. Okay, that's it. Thank you.
Thanks. Very, very interesting talk. Just a small thing. So suppose you start with a weighted connected graph. And as you're doing this basis exchange of the spanning trees, you pick the next edge according to its weight, not uniformly. So will you still get the same sort of...
Yes. So that will still be strongly log-concave.
Yeah. So, I mean, the idea is that you ask about application. So you might compare
It will not be as fast.
That's quite a complicated algorithm. Your algorithm is much faster than code.
That's true. But yeah, it's not as fast as Wilson's. Well, in the worst case, I think it has the same running time. But yeah, in general, Wilson's is sort of faster than cover time. This is basically still like cover time. These Markov chains are known to be sort of not that fast, but I mean, it generalizes to like all matroids. So, yeah.
My question, did you look at the distributions that are almost log-concave in some sense? I mean, is there a continuity here?
That I don't know. I'm very interested in that, especially in our proofs. So log concavity is only used in the base case. Our proof is the induction. The base case uses log concavity. The induction step uses the closure property. So in some sense, if the base case is weakened, you have something close to log concavity but not quite, in principle, it should still work. Although I don't have anything sort of any particular application in mind.